Hello everyone and welcome to another video on discrete time LTI systems. In this video we're going to consider a causal LTI system with input x of n and output y of n, and the system is defined by the system function h of z shown here. The input in this video will be a complex exponential with frequency omega 0, and it's applied suddenly starting at n equals 0. We describe that by multiplying e to the j omega 0 n by the unit step function u of n. And the question we will answer in this video is, what is y of n? So we're going to go through two different solutions. First, how do we find y of n analytically? And that gives us some general insights into what we should expect solutions y of n to look like. And then we're going to tackle the problem of how do we find it numerically, and that will give us some ideas about how we would practically implement this system, where we could implement this system so that it could take in arbitrary inputs, x of n. Okay, let's consider the analytical solution first. So I've just recopied the system function here. The system function is generic, and it has, in general, two poles, one at P1 and one at P2. And so the analytical approach is we first find x of z, the transform of the input, then we compute the multiplication of x of z and h of z to get y of z, and then we take the inverse transform to get y of n. So if we look at the input is of the form e to the j omega 0 n u of n, and that is the same form as a standard pair that we have, that standard pair being a to the n u of n, which we know has the transform 1 over 1 minus a z inverse, with the region of convergence z greater than a. So in this case, a is simply e to the j omega 0, right? And so this transform just becomes 1 over 1 minus e to the j omega 0 z inverse, where z, the magnitude of z, is greater than 1, because the magnitude of e to the j omega 0 is equal to 1. So the magnitude of our a in this case is equal to 1. Okay, so we have that, and then we can just multiply this transform by this transform, and that gets us y of z. Now we could ask ourselves, well, what is the region of convergence? Well, the region of convergence, we can write that out for each of these terms. We know the region of convergence for this term is z greater than 1. The region of convergence for this term is magnitude of z greater than the magnitude of P1. And this term, the magnitude of z, is greater than the magnitude of P2, the second pole. In general, P1 and P2 can be complex, so that's why we're taking their magnitudes here. And so the overall ROC, right, and well, first of all, why are these greater than P1 and P2? Remember from the previous slide, right, we had denoted that this was a causal system. So the causal system has to be the right-sided system. A right-sided system has a region of convergence greater than the poles. So each of these poles is, the region of convergence associated with each of these terms is this. And so then the region of convergence of the whole thing is z greater than the max of 1, the magnitude of P1, and the magnitude of P2. Okay, because it has to be the overlap of all of these, right? So that'll be z greater than whatever the maximum value is, whether it be 1, the magnitude of P1, or the magnitude of P2. Okay, so continuing our derivation here, now we have this y of z. And if we assume, and we're going to for this video, that P1 is not equal to P2 and is not equal to e to the j omega 0, so that we have simple poles here, we don't have any repeated poles, then we know we can use the partial fraction expansion, right? We're just doing partial fraction expansion here. We know we can do that, and we get one term for each. And then all we have to do is solve for the a, b, and c coefficients. So let's solve for a, first of all, right? So if we do it by our standard method, right, we cover up this pole, and we're just left with a is equal to the remaining two terms, 1 over 1 minus P1 z inverse times 1 minus P2 z inverse. And we evaluate that wherever at the value of z inverse that will make this go to 0. right? So that would be e to the minus j omega 0. Z inverse is equal to that, or z is equal to e to the j omega 0. Well, if z is equal to e to the j omega 0, we're effectively evaluating h of z, right? This is just h of z now, because we took out this term. This is h of z evaluated at z equal e to the j omega 0, and that's just the discrete time Fourier transform evaluated at the frequency of the input signal, right? So and we're using the relationship here, that there is a relationship between we're using the relationship between the z transform and the discrete time Fourier transform. And similarly, we can solve for the b and the c coefficients, right? The b and the c coefficients we're going to do the same way via our standard partial fraction expansion method, and I've written that out here. And so we can get a, b, and c, and then proceed with our solution. Okay, so now we went to here, we solved for the a, b, and the c coefficients, and now we just have to inverse transform each of these terms. And keeping in mind, right, that we have the region of convergences that we developed before, right? The region of convergence associated with each of these terms is, in this case, it's z greater than 1. In this case, it's z greater than the magnitude of p1. And in this case, it's z greater than the magnitude of p2. So we have those three regions of convergence for these three different terms, and then we can easily take the inverse transform because they all fit that standard form that we have available to us in the table. So the result will be y of n is equal to a e to the j omega 0 n u of n plus b times p1 to the n u of n plus c times p2 to the n u of n. And so that's our general solution. And again, we would have, depending on what we had for omega 0, p1, and p2, we would have numbers to plug in for a, b, and c. Okay, so now we have what was written out before, but now I've taken it one step further, and I'm just going to say, okay, let's imagine we know that p1 and p2 are just, in general, some sort of complex number. So we could write them as r1 e to the j theta 1 for p1 and r2 e to the j theta 2 for p2. And obviously, if they were real numbers, then theta 1 and theta 2 would be either 0 or pi to put them on the real axis. But in general, they can be complex numbers. And so if we plug in, we can plug in a few more things. One, let's plug in our expression that we derived previously for a, and that will be just the value of the dt of t at omega 0, right, times e to the j omega 0 n u of n. And then we get these two terms, right? Instead of p1 to the n, we get r1 to the n e to the j theta 1 n u of n, right? And then c times r2 to the n e to the j theta 2 n to e to the j theta 2 n u of n, right? So what we have is the first term resembles the input, right? That resembles the input that's being forced. That's the input into the system, but now scaled by the frequency response at the frequency of the exponential. And then we have the two terms associated with the system poles. And this works for any second order system, right? We didn't assume a particular value for omega 0. And we didn't assume a specific value for the poles. We just assumed that we could write them as r1 e to the j theta 1 and r2 e to the j theta 2. So this response of an LTI system, a second order LTI system to a suddenly applied complex exponential, has these two parts. One resembles the input, and it's scaled by the frequency response at the frequency of the exponential, and the other are terms associated with the system poles. So this is the same solution as written on the previous slide, but this is, if we look at this is a steady state solution, right? And it looks basically like response to an eigenfunction. If we didn't have the u of n here, and we had e to the j omega 0 n going in for all time, the output would just be h of e to the j omega 0 times e to the j omega 0 n. All right. It isn't going in for all time, so we're going to end up with a u of n here. But now we have this second term that depends on the system poles. If the system is stable, then we know that the poles for a causal system are inside the unit circle, meaning that R1, the magnitude, is less than 1, and R2, this magnitude, is less than 1. Okay, if raising something that's less than 1 to the n is going to lead to a decaying exponential as n goes to infinity. So these terms die away. So this would be our steady state response, and this is a transient response. And the length of that transient response is determined by where these poles actually are. So very often we visualize the system function h of z by sketching its pole zero diagram. And here I've just sketched the location of the poles for this system. For this particular system, we would end up with two zeros located at 0. But I haven't sketched those. I've just sketched the poles, P1 and P2. Now, I've sketched them so that they sort of look like they're complex conjugates of one another. That isn't necessarily required for this form of the solution, but that's how I've sketched them. So the location of the poles inside the unit circle, right, is going to tell us how long it takes this transient response to die out. If the pole has a radius associated with it that is very, very close to 1, say it's 0.99, 0.99 to the n is going to take a lot longer to die out than 0.2 to the n. So if the pole were here versus out here, it's going to take a shorter time to die out here and a longer time to die out here. So the location of those poles, their radius inside the unit circle, tells us how long it takes this transient response to die out. Now this pole zero plot we know, so I guess I should, strictly speaking, draw the zeros on there. There's 2 zeros at 0 for this particular system. So this pole zero plot provides us information about the frequency response. In other lectures, we've studied how to sketch the frequency response given a pole zero plot. But we've also just seen that this pole zero plot effectively provides us information about this transient response of this system and how long we would expect that transient response to take to die away. So the pole zero plot is very informative about what the system's behavior will be. It tells us a lot about the frequency response, which is going to tell us how it's going to weight, how it's going to scale this complex exponential input. And then it tells us about the time response of the system, meaning how long it will take the system's own sort of natural response here due to the poles to die out. Okay, so we talked about wanting to study, how would we solve this numerically? We've just come up, given that we know the exact pole locations and given that we know omega 0, we could derive an analytical solution to this. But how would we implement this system numerically so it could take an arbitrary exponential input? Well, we would do that by first finding the difference equation. We'd find the difference equation. We have h of z, which is y of z over x of z. We can do the cross multiplication here. We get this form, y of z times the two pole terms is equal to x of z here. And then we're just we're doing the multiplication through and combining some terms. And then we can inverse transform this equation, remembering that z to the minus n0 corresponds to a delay of n0. So this y of z times z inverse is y of n minus 1. Y of z times z to the minus 2 is y of n minus 2. And we have these two coefficients. And then on the right-hand side, we just get x of n because there was just a 1 in the numerator here. And so we could rearrange this and we would get the difference equation, right? Moving the previous values of y to the right-hand side, we get y of n is equal to x of n plus p1 plus p2 times y of n minus 1 plus p1 times p2 times y of n minus 2. Now, we can solve this iteratively. We do have to assume initial conditions, but for an LTI system, the for the system to be strictly linear and time invariant, we have to assume initial rest conditions, which means that nothing is happening before the input comes in. So all of these previous values are going to be equal to 0 until the input comes in. So let's summarize a bit about what we've learned about this example. So we started with a causal discrete time LTI system, which had a complex exponential input suddenly applied at time n equals 0, and we solved for the output. And we did that solution two different ways. One, the analytical solution, which resulted in this form, and a numerical solution that resulted in a difference equation that we could use, that we could iterate and solve iteratively for the output y of n. We know that h of z, the system function, can be effectively described by a pole zero plot to within a scaling factor at least. And I guess I should put my 2 zeros right on there. So those are the zeros there. And so this is the pole zero plot. So if we have h of z, that gives us the pole zero plot. That gives us insight into the frequency response, which is essentially the scale factor that's going to get applied to the complex exponential input. And then it gives us information about where the poles of the system are. So it gives us the form of these terms over here, and gives us an understanding of how long it will take those terms to die out. And that's fundamentally determined by R1, the radius of the first pole, and R2, the radius to the second pole, right? The phases certainly matter for the exact solution, but what determines how fast they die out is just how far out the poles are, how close to the unit circle the poles are. So this expression and its corresponding pole zero plot really do give us a lot of information about what we expect the solutions to this problem to be, and a lot of really great insight about the system. So that concludes this video. Note that this was a pretty general problem that we were solving. It just involved two poles at arbitrary locations, P1 and P2. We did assume that the system was causal, and we assumed, but that's really the only assumption that we made here. And you could easily see where we could extend the solution. If we had more poles and more zeros, that would just change the number of terms we had in our partial fraction expansion. So it would change the number of terms we'd end up with here. But this is a sufficiently general solution that you can solve harder problems involving more poles, and at the very least get some great insight into what the forms of those solutions would be. If we had more poles, that would just add more terms here. And so it would further affect the transient response and how long a transient response we would expect to see. And it would also affect how many delays we would see in our difference equation implementation. So that concludes this video. I hope you found it helpful. Thanks for watching.